Good morning and welcome to today's webinar on eTrax. eTrax essentially is a solution for the analysis and operation of rail systems. Today's webinar essentially will be somewhere between 30 to 45 minutes and the agenda will include the following items. We'll go over some of the key industry requirements. We'll go over the solution overview. Uh, we'll go over essentially the features and capabilities, kind of summarize them for you. We'll take a look at an example using the eTrax software and run through some simulations. We'll talk a little bit about the real-time traction power management system, the product offerings, essentially what's in the package, and essentially a summary at the end. There will obviously be a chance to ask question and answers throughout the webinar, but we'll be taking most of the questions at the end of the webinar. So first, let's start with the key industry requirements. Usually when we're doing traction power analysis, we would like to essentially understand what is the substation capacity that's required for either existing or planned train operations. And obviously we want to have some linkages between the train timetable, the energy demand on the system, and obviously the energy cost at the end of the day. So how many trains can I run in a specific day or in a duration at the same time without essentially hitting my peak demand and impacting my energy cost tremendously? How can I essentially manage that, and how can I do all my what if analysis? The industry also lacks some level of centralized information about their electrical power system. The validation and predictive simulation capabilities do exist in certain softwares. However, they're not as graphical or user-friendly as the industry would like them to be. Finally, the system or the software should be able to do some infrastructure design or optimization, such as the design and placement, configuration, and decide on the equipment ratings. Now, some of the other requirements that are a little bit more extensive include doing what-if analysis with different rolling stock, or essentially which locomotives and which wagons or consist or coaches should be used, and what impact do they have on the electrical demand in the system. When you're running through the timetable, are you hitting any capacity points, pinch points, if you may, where the voltage drops are too large that impact the performance of the train as it's running through the system? And essentially, how do you deal with unplanned events, such as a circuit breaker opening midstream during a simulation, and it impacts the voltage drop in the system in general? So these are essentially some of the requirements from the industry. Now we'll talk a little bit about the solution. We essentially got a lot of input from the industry regarding the requirements, and we essentially put together eTrax as a solution for the design all the way through to the automation of AC and DC rail traction power systems. And it's essentially a tool that's used to understand the operation of the traction system all the way from the train timetable down to the actual electrical demand, not only on the traction power system, but as well as the upstream sub-transmission network as well. So you can essentially use eTrax to solve transmission, distribution, traction, and low voltage signaling systems together. It's obviously developed under the ETAP QA program. It utilizes industry accepted train performance equations, and it's been verified and validated against field measurements and hand calculations. So with eTrax, you can do a lot of different types of simulations. You can evaluate the substation location and capacity, centralize your database, model events and any future expansions in the system. It's an unbalanced solution, so you can also understand what is the impact on the voltage and power in the system as you are performing the simulation. And finally, it couples on to the existing ETAP real-time architecture or infrastructure that we have to essentially allow you to go all the way from model design to automation of the electrical system. So as far as the traction solution is concerned, here are some of the main groups or items that are included as part of eTrax. We've essentially developed specific traction equipment models and provided modeling capability and simulation capability for traction elements like auto transformers, booster transformers, and so on. We've taken advantage of geospatial diagrams and the existing single line diagram that we provide within the ETAP software. We also include routes and timetables that can be defined and created into multiple what-if scenarios. There is an existing rolling stock library that you can use to model different types of trains in the system. Train performance calculation that essentially converts the mechanical system, the mechanical train system, like the track bend radius, and so on, into electrical information, or essentially the load demand on the traction motors in the train. There's a full unbalanced time series or time domain simulation that gives us the power flows in the system. There's operation optimization routines that are built into the program, and then it finally couples in with the SCADA or the power management system as well that ETAP offers. So let's talk about the features and capabilities very briefly. Here are some of the capabilities that we'll be looking at. Given the time frame, we'll focus on a few items, and then we can obviously schedule different webinars for additional information. So essentially, it's a full AC/DC traction power simulation where we are considering the geospatial, the logical, that's the single line diagram, thermal, so you can also do underground raceway calculations, as well as functional views. There's different traction transformers that you can utilize, build-in traction substations using our templates, include information from the rolling stock library, and then from the calculation perspective, you can perform unbalanced power flows, fault calculations, train performance simulation, substation grounding and potential, energy calculations, and again, the linkage with the real-time system. On the safety and protection side, you can also utilize the switching sequence management, where you can understand the effect of different breakers opening and closing in the system and its impact on the network, AC and DC arc flash from the substation perspective, protection and coordination, as well as earthing and shock protection for the low voltage system. So with that, I'll jump straight into the actual program itself. And what we will essentially take a look at is the traction toolbar right here. So this is essentially a brand new toolbar that we have included essentially in the geospatial single line diagram, where you can simply drag and connect things together and build the track information. As we're building the track information, we can also go ahead and place different components into the system, like a train station. I can go ahead and add another one right here. Obviously, there's no limit. You can build as many tracks as you would like in parallel, and they can be of any length in the system. There are various tools also provided inside the program where you can quickly figure out what is the measurement or the length of the system that you've just built. So I've just constructed something that's about 1 kilometer long. On this toolbar, we can also add things to the program, like a platform, and I want to essentially insert a platform right here as well. So as you can see, it's fairly graphical and very simple to essentially start constructing various things onto the track segments. Here I've just gone ahead and added a signal. I can add speed limits, level crossings, and so on and so forth. And as usual with ETAP, you can double click on any specific component and define the properties or the details. So this is information for a signal. here I can go ahead and define the speed limits for different types of trains, like a freight train or passenger train, and so on. So here what I'm essentially doing is building the geospatial layout of the system. Now, if it is a new system and the geospatial layouts are not available, that's okay. You can still essentially utilize this view to create the network or the rail system and then generate the electrical diagram from this. One other neat feature that we have inside the geospatial diagram when we are editing the model is I can simply build things with very odd bends, and obviously we all know that railway lines don't bend this manner, they curve. So I can essentially add points into the system like bend radiuses, and then ask the program to essentially reshape the tracks in a more appropriate manner. So here I'm going to go ahead and add another bend radius, so you can see these are my bend points. I can essentially right click and reshape along the edge. So very easily I can build my railway geospatial layout, and all the computations as far as the distance and the bend radius, they're automatically being tracked inside the program. So these don't need to be entered in a manual fashion. So I'm going to go ahead and open up a project file that I've previously built inside ETAP. And in this particular model, what we will essentially see is the geospatial layout, which is now on the right-hand side. And I will zoom out so you can see it better. So wherever you see the rectangles, we are essentially showing the train station. We can see the geospatial layout of the railway lines. It's a little bit more comprehensive, a little bit more complex system. And from this particular system, what we have done is essentially automatically generated the single line diagram as well. So the blue rectangles that you see here, I can essentially find them onto the geospatial view. So I can essentially go to the next train station on my geospatial view and then find it in the corresponding single line diagram as well. So with that kind of concept, you can essentially maintain the geospatial view and the single line diagram synchronized essentially at all times. Once the synchronization is done, then the main effort is really to model the electrical connections or the source or the power supply to this network. And they can essentially be modeled using the various components that we have on the ETAP element toolbar. So when the single line diagram is generated in the system, we essentially utilize our standard components to build the power supply of the network. Alternatively, you can also go into the templates that we have inside the ETAP. These are essentially the substation templates. And we can use these templates to model or bring any other piece of information in. So I can model a substation, a typical traction substation, and then drop it into the single line diagram and connect it to my TraX. And that's essentially what I've done inside this system already. So we have a switching station right here and essentially a traction substation here that has been connected into the respective TraX. The data entry for each of these components remains as it is. These are typical ETAP component editors. So we can essentially go about make these changes inside the system and start populating the single line diagram. So once the single line diagram essentially is populated, the next step for us is essentially to start defining various characteristics of the track, the overhead wires, as well as the rolling stock that's being used in the system. So for that, you can either go to the geospatial view, or you can essentially go to the track onto the single line diagram and then define the specific details for each of these sections. So I'll essentially open up our track editor right here. So you can see some of the details. So I have essentially different track sections that are running from one train station to another train station. As you jump from one station to another, the program shows those to you in the geospatial view, or the single line diagram is your choice. All the objects that are created between these two stations are essentially listed in my view right here. And as usual, as you select any of these components, they are highlighted onto the geospatial view. If there are any speed limits, such as this one for 75 kilometers an hour, they show up automatically because that's what I had applied. The bend radiuses are calculated automatically, so are the segment lengths, as well as the grade, essentially the incline of the track. So this is all physical information about the track. I have certain buttons available here to update the track editor, or essentially the spreadsheet view. If I make any graphical changes, all I have to do is come in here and update my spreadsheet, and there's no need to essentially keep track of tabular data. Everything inside the program is done through a graphical interface. The next portion that essentially we would have to do is make sure that we are defining the routes. So as the train is essentially going from one train station to another train station, we can essentially stitch multiple sections together and make a train route. So I've just selected another route here, and as I go through my selections, the program essentially is highlighting those routes for me. You can also choose to color code the system based on the route-based coloring. That can be actually done using the theme manager. So I can come in here and say, color all my routes in a different color, so I can see how the train is being routed through different train stations. So I'm going to go back to my editor here so we can see all the different routes in the system. And essentially the distance is the complete route length. So as the train is going from this train station all the way to this one, here are the individual lengths that it goes through, and this is the total distance. Again, all of these values are being calculated automatically through this geospatial diagram. Once you set the scale correctly, all of these distances are automatically tracked by the program. The next thing I would do for the route is essentially define the timetable. So again, here the program allows you to select for each route as many timetables as you want to generate. So I can essentially quickly come in here and generate a timetable for this route. I can specify that this timetable applies to different days, whether it's a holiday or a weekday, weekend, the direction that the train is going to take. And then I can start populating the number of trains. So if this route essentially is running 20 trains, and the prefix of the train starts something like this, the program will essentially create my train names for me and essentially define the number of trains. So 20 trains that I can fill in here. Now this can be filled in manually, which may be a daunting task initially, but you can also ask the program to either generate this timetable, or you can actually import a timetable from an Excel file. So both options are available. The Excel import option is available here. We utilize a specific format in Excel to import this data, so making, again, the data entry very fast. And that's the main goal. We are essentially trying inside this application to make the data entry go faster, so essentially saving you time overall in executing the projects or the studies. So once the train schedule has been defined in some fashion, our next step is to define the types of trains that are being run or utilized on this particular track system. So here in this file, I've defined 4 different configurations. Each configuration essentially can be a locomotive or a EMU or electromotive unit, or it can essentially be a locomotive pulling a number of coaches or wagons in the system. All the data for the EMUs or the locomotives essentially is coming from the rolling stock library, so I can click on the library button and pick the manufacturer and the model. So again, those of you who are familiar with ETAP will recognize this approach. It's fairly straightforward, easy to learn. So you can easily pick the manufacturer and the respective EMU. Obviously, in ETAP, all the libraries are user definable, so you can essentially even add your own or request us to add the library information in for you. So once we define the train configuration, and that's again very straightforward, you can create a new configuration and define essentially the manufacturer and start defining the number of coaches that you want to utilize. The next step for us would be to then combine the train schedule and the train configuration together. So the schedule tells me which trains are running at what time, and these are the train numbers or the ID of the train. The configuration tells me what type of train am I running. So therefore, I have another table that combines the two pieces of information together. So this particular train number happens to be this type of train. It's this configuration. So it's the program is fairly flexible. You can have every single train that runs in the system be a completely different configuration. It has that level of flexibility. But obviously, in most networks, there are a few configurations that are typically run. So it makes it much easier to do this assignment. And again, most of the assignment is graphical. You can select one and essentially apply to all, or do a group selection and make the train assignments. So essentially, all of this information was plugged in to make sure that we are able to run this particular system in a simple manner. So I'm essentially going to go ahead and open up this example file again very quickly. So we can essentially see just one single view instead of seeing them side by side. So I have my same system loaded back again, two views side by side. I'm going to go ahead and close the geospatial view for a second and focus on the single line diagram right now. So on the mode toolbar in ETAP, we've added a new icon for traction power systems. And essentially it has very specific types of studies that you can use, including bringing up the track editors, the train schedules, change the display options, and essentially also go ahead and define the solution parameters. So I'm going to go ahead and do that. I'll open up the solution parameters real quick so you can see some of the capabilities here. Obviously, we're running a unbalanced power flow in this system. We can also allow the user to select which timetable we want to utilize. You can choose to run a specific timetable on a specific route. You can easily swap between multiple sets of timetables that have been defined for a route, making the what-if analysis definition very, very easy. You can also choose to run the complete timetable or just run a specific time period. So I'm going to run the complete timetable in our case. There are alerts obviously inside the program as well that allow you to define overloads or over voltages in the system. Because we're running an unbalanced power flow, we also have alerts for voltage and current unbalance. And then you can also choose which components or devices you would like to see in a graphical manner or essentially in a plot. And finally, we can also define certain sequence of events or actions that are unplanned or essentially part of the simulation that affect the movement essentially of the train. So I'm going to go ahead and run our simulation here. And what I'm essentially doing is running about 200 trains in a 2 or 3 hour period with a full system calculation, which means the program first looks at the timetable. In this case, that's how I've set up my option. It looks at the timetable. It essentially accelerates the train in the system based on the limits that have been provided, such as the speed limit, as well as the time frame in which the train must go from one station to another station. So it's essentially solving the train performance calculation equations in the background, and then sliding the load across the rail. And as the train is sliding across the rail, the program's constantly calculating the voltage drops throughout the sections, because the impedance is changing as the load is moving away from this particular substation. And all of this information is then being impacted onto the substation bus, into the network, into the main system. So all of this solution is essentially happening in parallel, or it's happening simultaneously. So we essentially have multiple iterations essentially running in the background. So while that is running, I'll explain to you what's happening internally. We're taking the track information, such as the grade, the bend radius, the rolling resistance, acceleration resistance, so on and so forth, to essentially define what the load on the traction motor is. We obviously have information about the rolling stock itself, such as its weight and the area of cross section and the type of traction motor it's using. That essentially goes into a train performance calculation. The input to that also is a train timetable, and essentially in the future it would be the signaling data as well. From there, we essentially generate the actual speed profile of the train, how essentially it's going to accelerate, decelerate, go through regenerative braking, and so on, and then pass that information on to ETAP for the user to visualize. So if you go back to our system, the calculation is actually now finished. And what the program is now showing me is information onto the single line diagram, essentially where the different trains were initialized, which train stations they were waiting on when the simulation began, and what are the initial voltages in the system. So I have about 23 kV or so on this bus bar before the simulation begins. Now I can obviously move this time slider and start moving in time. My duration is from 3 o'clock, 3:30 on to about 6:40 p.m. And right now I'm looking at the results for about 3:45. And as I slide through, you can obviously see the results running through the single line diagram as function of time. Because you're seeing this over the web, you may see a little bit of delay on your side, but the results essentially move very smoothly onto the actual desktop PC. And then from here, I can choose to show the units. I can go in here and switch over to show actually megawatt information instead of kilowatts. So here I can see about 10 megawatts that are being pulled by the train from this specific transformer based on various trains that are running in the system. You can also actually have the program just play back the information for you. So I've set the playback rate to about 1 second, and then in this manner I can just sit back and visualize and see what is going on with each and every train in the system. So I'm going to go ahead and essentially just focus down here, so we can see one of the trains. It's moving at about 47 kilometers an hour. The second number you see, 3.6, 3.7, increasing is the distance as it's moving away from the train station. And essentially the last number is essentially the grade or the incline of the system, which is pretty much zero in the system. So here we can see this train is now slowing down. It's arriving at this train station and its speed is reducing down to obviously 0 kilometers an hour. It will wait for the dwell time that's been defined for this train, and then once the dwell time is complete, this train essentially will take off and head off to the next train station that it's supposed to go. You also have the choice of essentially locking down onto a train. So if I'm just interested in seeing what is this train doing in my system, I can just click on it, and then the program will essentially move the entire diagram, keeping that train in focus. And you can see from a single train's perspective what is going on with this train. You can also change the display options of the train results from speed, location, elevation to specific information such as energy, tractive effort, acceleration, or you can also show resistance like rolling curve and acceleration resistance. So a lot of different choices. Here I'm seeing the energy buildup or the energy consumed by this train in the network. So from a visual perspective, you can see this data on the single line diagram. You can also ask the program to show this information to you on the geospatial diagram. So I'm going to go ahead and hit play again, and we can see the same information that we see on the one line with the trains essentially at their respective locations, also reflected onto the geospatial diagram. So you can literally see when the bend resistance is increasing, you can relate it to the geospatial diagram as well. So a lot of graphical niceties that have been included with the train program. For those of you who may not want to see this information through a time slider point of view, you can also see the same information through the plots. You have a choice of either seeing the substation information or you can see a specific train going through its entire trip. So if I pick one train at random and I want to see the voltage at the pantograph of this train, I can plot it and just zoom into the specific duration that this train ran from one train location or one station to another station. So this is one example of looking at specific information coming out from the program. You can also go to a bus, and let me pick the specific bus 98, and I want to see the voltage on this bus in the system and plot it. So here bus 98 happens to be one of the buses on my traction substation, which is right here. And what I'm actually visualizing is a cumulative impact of multiple trains running in the system. So you can see how the voltage is essentially fluctuating in the system, and you can see where the peaks and the valleys are in the system. So we can see the lower voltages approaching 22 kV, but on the peak side they're almost approaching 23.7, 24 kV when the system is unloaded or most of the trains have stopped. So this gives us a very nice representation of where the voltage swings are in the system, and it also allows us to understand where to place booster or auto transformers or even additional traction substations to improve the voltage drops in the system. Now, from a data perspective, when we looked at the track, when we look at the track, we look at the track and the overhead wire, or essentially the catenary information. So essentially the data entry for the track impedance and the line impedance, they are actually done in one single location. So you don't have to enter in this data over and over again. We essentially set up what we call a warehouse, and inside the warehouse you can define the catenary configuration, how the catenary is laid out in a physical perspective, the coordinates of where the conductors are actually placed. You can specify the ground wire information if there is one. You can specify the phase conductor information, and then the program will essentially calculate based on the phase wire, the ground wire, and the catenary configuration, what is the actual impedance of the catenary system. There's also a track resistance or track impedance warehouse where you can define the electrical impedance of the track. And when we are essentially utilizing this in the program, all you have to do is very simply come in here and pick the information from the warehouse and apply it to the entire system. Since the overhead conductors and the track information doesn't really change much within the same system, you can define it in one section and then apply it to all the sections. So the warehouse essentially is a way of applying one single data entry that you've done in the warehouse and applying it to multiple locations without having to go through individual data entry in the system. So with that, we can essentially look at some of the additional information that we have in eTrax, such as the verification and validation. So what we've also done is we validated the results from ETAP against field measurements. So we've done validation for single EMUs, multiple EMUs, traction substation feeders. We've benchmarked the program against various locomotives and many other benchmarks. And these are actually against field measurements. And then we've also benchmarked the program against Senelec standards. So the program has been field tested and benchmarked against industry standards. Now, the other advantage of the eTrax system is the ability to connect with real-time data, which is where the power management system essentially comes in. So when we're looking at power management, it's essentially an integrated approach where we are looking at the sub-transmission information, the low voltage systems such as the signaling system, the AC and DC traction power itself, the overhead catenary and the power applied at the pantograph, the protection and the control at the substation, the auxiliary loads, which is essentially the terminals or the train stations themselves, the traction substation, the rolling stock, and the interlocking. So we take all of this information together in real time and bring it into the eTrax system. So the benefit obviously is we use one integrated control system that makes it a common interface for controlling different parts of the system because they are interconnected. That essentially ensures you have a coordinated response whenever there's an emergency situation. And then it makes sure that all the data is in one location in a centralized database. And because it's built on the existing ETAP software, you're essentially expanding the capability of the existing license that you have and adding the simulation as well as the real-time power management capability onto the same platform. So it essentially accommodates the expansion of the business. If you're adding additional tracks in the system, makes it a whole lot easier to manage and maintain in the system. So when we are essentially bringing real-time data in, what we are essentially doing is things like model validation. You can utilize the real-time data to further validate the results that are coming from the simulation program. You can use model-based alarming. So in areas of the system where you don't have measurement, you can actually still alarm components that are being overstressed. You can essentially do model-based monitoring, so you can get a geospatial status as well as the electrical status of the train together in one system. You can essentially do predictive analysis, which means what is the impact of a new timetable on the train operation. So if I intend to change the timetable tomorrow, what kind of impact will it have given how my system is operating at this point in time? And then if the sub-transmission topology changes, let's say there's a loss of substation because of a fault somewhere in the sub-transmission side, what would be the impact onto the train operation? And then finally, you can also replay the sequence of events later on if there was an emergency condition and the system did not react the way it should have. You can utilize the historian that ETAP provides to replay the sequence of events and take that information into the simulation calculations. You can also utilize contingency analysis to see where the weak points in the system are. That could be single or double contingency itself. The switching work order can be used to essentially evaluate the switching plan. Uh, so what the employees essentially intend to do with the equipment can be generated into an actual work order, simulated against the actual train operations, validated, and then passed back on to the employees to physically make the change in the system. So it essentially acts as a very good validation tool before you take any action in the system. And then the most important of them all, which is energy accounting. So it keeps track of energy demand and cost for all possible train schedules, not just the ones that are running. And the main objective there is to see the impact of various timetables that it has on the operating cost of the system, and essentially what is the best way to reduce that peak demand in the system. So that application essentially is very beneficial. So in summary, um, what we provide in eTrax is essentially a power system simulation tool that has a train performance calculation that takes the train movement into electrical demand. It converts that electrical demand into the impact on the entire network. So we solve the entire train system and the upstream network together. There are planning tools like load flow and short circuit and protection to make sure that the system is designed and is operated safely. A geospatial representation to get a perspective where the trains are actually located and where are the assets in the system with relationship to each other. You can bring in real-time data and do some real-time or online simulations of the system, as well as cost optimization. And then there is a SCADA component for data acquisition and mobile views that can actually give you summarized information onto your web page or the phone. So essentially, you would end up utilizing eTrax for data centralization, overhead catenary design, geospatial asset visualization, the supply design and substation sizing, protection, ground grid design, coordination, and so on. Mechanical to electrical demand calculations, impact of different rolling stocks in the system, and so on and so forth. So essentially, it's a solution that goes all the way again from transmission down to the low voltage signaling system in one software. So given we have limited time, we'll essentially conclude our presentation here.